Hi everyone. Today we're going to be looking at Hess's law in section 5.4. The reason for the development of Hess's law is due to the limitations of calorimetry. If we can recall, many reactions release too much energy to be performed safely within a simple calorimeter. As well, simple calorimeters are usually used only for processes involving dilute aqueous solutions. And so, in addition, many reactions occur too violently or too slowly for the calorimeter method to work. However, chemists found and were able to determine that the enthalpy change of nearly any reaction by using some accumulated data as well as Hess's law. So the solution to these limitations of calorimetry was the additive enthalpy changes, which eventually became known as Hess's law. So scientists discovered that the enthalpy change for any reaction is going to depend only on the products and reactants and is independent of the pathway or the number of steps between the reactants and the products during the reaction. So a good analogy is taking a look at the pathway of two cyclists going down a mountain. Both of them start at the top of the mountain, and both of them are going to finish at the bottom. Each cyclist has a different path, and the routes that they're taking are independent of the gravitational potential energy. All right, so the overall height from point A to point B is still going to be the same, regardless that one took a very wavy path to get to the finish line and the other cyclist B, took a more direct path. Similarly, enthalpy change is not dependent on the pathway of a system, just like these two cyclists are not. So we can see that this analogy can be applied to chemical reactions. So let's consider carbon dioxide. We know that carbon dioxide can form from carbon and oxygen by using two different pathways. So number one, which is pathway one, is a two-step process. Carbon can react with some oxygen to produce carbon monoxide as an intermediary step. That carbon monoxide that is produced continues to react with some more oxygen in the reaction vessel to ultimately form my carbon dioxide. Each one of these reactions, we can calculate their delta H values respectively. Now in my second pathway, which is number two, carbon can react in one step directly, where it forms from carbon plus oxygen to produce carbon dioxide. Its delta H value is negative 293.5. If we look at these two reactions, we'll notice that pathway 1, if I add up the two delta H values, is going to equal negative 293.5. Thus, in both cases, the net result is that 1 mole of carbon reacts with 1 mole of oxygen to produce 1 mole of carbon dioxide. So it's the sum of the enthalpy changes for the first pathway is going to be identical to the enthalpy change of the second possible pathway. So this was a very important thing that was discovered by chemists, which we could use then when we were not able to use calorimetry in the lab. All right, so again, looking at it graphically, if we look at carbon plus oxygen using one path, or we have carbon plus oxygen forming carbon dioxide and then it reacting with some more oxygen in a two-step process. In both cases, the enthalpy change is negative 393.5 kilojoules. So regardless of the pathway, the enthalpy change for this particular reaction is going to be the same. So Hess developed it into a law, and he states that the delta H value for any reaction that can be written in steps is equal to the sum of the values of the delta H for each of the individual steps. A very important law that we can use. So after performing over many experiments, each time and it didn't matter which reactions we looked at, this law applied. Now we can use this law to calculate enthalpy change of any reaction using two different methods. We're going to learn about today's method, which is combining these equations algebraically. And then in the next lesson, we're going to look at how the standard enthalpies of formations are used, as well as Hess's law. So now let's take a look at this example. We can combine the two equations. These equations 1 and 2 are called our given equations. These are tabulated, so they would have to be given to you in a question, or you would have to look them up in a reference table. Equation 3 is called my target equation, the one that we ultimately wish to determine the enthalpy change. So you'll notice equation 1 and 2, we know the actual delta H values. Those have been already determined experimentally. So let's take a look at how we can apply Hess's law to this particular reaction. So first off, always start your questions by writing out the target equation. So in our case, it's the decomposition of hydrogen peroxide, H2O2. And it's going to produce half a oxygen molecule and one water molecule. All right, next thing to do is list both of the given equations. So the first one that we're given is H2O2 is going to form H2 plus O2, and we're told that this delta H value, which we're going to call delta H1, is positive 188 kilojoules. The second equation is H2 plus half an O2 molecule is going to form H2O. And we see that that has a value of negative 286 kilojoules. So this we call our target equation. So what you want to ensure is that by looking at each of the individual equations, is the reactants and products on the correct spot? So if we look here, my reactant here, H2O2, in this first equation, both of them are on the reactant side, and both have 1 mole of it. So I'm going to leave this equation as it is. So we're going to leave equation 1 as it is. We also notice for the second equation, it contains the H2O. The H2O in the target equation is part of the products. Likewise for equation 2, it too is part of the products as well. And both of them have the right coefficients of 1. So what this leaves me to do now is add them up. We're going to sum up these two equations. So anything on the left side can cancel with anything on the right side of both equations. So you'll notice that I got an H2O on the right side and an H2O on the left side. So I can cancel them out. As well, I have a half a oxygen molecule here, a full one here, so I can cancel out a half of it, leaving a half. Okay? Nothing else can cancel out. So now I go ahead and I add up the two equations. Now we're going to sum the equations up. So what I'm left with is H2O2 liquid, and I have half that oxygen molecule from equation 2 plus my H2O. Now that I've added these two equations, 1 and 2, I have achieved my target equation. It looks exactly the same. So therefore, I've achieved what I wanted to. Hence, what I can do now is I can sum up the delta H values. Okay, so this is the target equation. So now we can sum up the delta H values from the two equations. So delta H for this particular reaction is delta H1 plus delta H2, and that is going to give me the delta H for this particular reaction. So I got positive 188 kilojoules plus negative 286 kilojoules. So please be careful with your arithmetic. Make sure you're adding these correctly. So what this gives me for this particular reaction is negative 98 kilojoules as your final answer. So if we look at this graphically, we see here that hydrogen plus oxygen is going to form my H2O plus half my water molecule. All right, so by combining equation 1 and equation 2, we are going to get equation number 3. All right, it's the sum of the two of them together. So if we look, we didn't really actually have to do very much mathematics in these equations. However, in many cases, we do need to manipulate the equations before we go ahead and add the delta H values. So we need to make sure we remember these two rules. These are two rules in which we can manipulate our given equations. We can reverse the equation so that the products become the reactants and the reactants become the products. And so whenever we do flip or reverse the equation, we must change the sign of the delta H value by multiplying it by -1. The second way in which we can manipulate an equation is by multiplying the coefficient in the equation, each coefficient in the equation, by the same integer or fraction. When you multiply the equation, you must also multiply the delta H value by that same number. All right, so very important rules that we need to follow in the next more complex questions, because they won't be as easy as the previous one. All right, so let's take a look at this next example, example number 1. We want to find the delta H value for the complete combustion of pure carbon. All right, so we are going to call this our target equation. All right, this is my target equation. Carbon plus oxygen produces carbon dioxide. So unfortunately, the student didn't have a calorimeter to perform the experiments. However, he did have a reference book containing the delta H values for the following two equations. So these now are my given equations. And their delta H values are known because they were determined experimentally. All right, so equation 1 is negative 110.5 kilojoules, and equation 2 is positive 283 kilojoules. So now, to add these equations algebraically, we need to make sure that we arrange them so that the reactants and products that we need for the target equation are on the correct sides of the arrows. All right, so we want to make sure that carbon and oxygen are the reactants, and carbon dioxide is going to be the product. All right, So let's take a look at this particular equation. So I'm going to write out the target equation because otherwise we can't, it's better for us to visually see what it is so that we'd realize what we're talking about. So we've got carbon plus oxygen forms carbon dioxide. All right, this is the delta H that we're looking for. All right, we have been given the following two equations. Equation number 1 that we found from the reference table is carbon plus half an oxygen produces carbon monoxide. And that we found in the reference table to have a value of minus 110.5 kilojoules. The second equation, and it's really important that we keep our arrows lined up, is CO2 gas. Lining up my arrows so I see what's reactants and what are products. CO plus a half of an oxygen molecule. And this reaction has an enthalpy change of positive 283.0 kilojoules. So we need to look at each equation individually to achieve my target equation. So looking at equation 1, it's the carbon that we're interested in here. All right, and carbon in the target equation are on the correct side. Both of them are reactants and both have coefficients of 1. So I'm going to leave it as it is. Okay, so I'm going to rewrite that as the equation number 1, as the equation as well. My delta H value stays the same at minus 110.5 kilojoules. Now, looking at equation 2 that was given, I see that my carbon dioxide is actually on the left side, but in my target equation, I want it on the right side. So I need to flip this equation. So I've got to flip it. And if I flip it, I also need to reverse my delta H sign. Okay, so that's what I'm going to do here. I'm going to flip this equation. So now I'm going to put CO as my reactant plus that half oxygen molecule, lining up my arrows, and then I've got carbon dioxide, and delta H2 this time is going to be negative 283.0 kilojoules. I changed my sign from positive to negative. Very important to remember that. All right, so now I can go ahead and I'm going to add up my two equations and see if I get the target equation. All right, so now that I have those, I am going to rewrite them down below here because I'm running out of space. So let's rewrite them one more time. So these are my two new equations. After I've manipulated them. So the first equation, remembering that I left it as it is, so this is equation 1, and then my equation 2, which is the one that I reversed or flipped. And keeping in mind, this is very, very important, I needed to change that sign. okay, to negative, because originally in the given equation it was positive. All right, so this is very important that I had to do that. Now I can go ahead and see what cancels. You'll notice that I have a CO on the product side, and it cancels with the CO on the reactant side. I go ahead and add these two equations. I can't cancel any other terms from the left and right side. Now I can go ahead and add them up. I got a carbon, and now on the left side I have half an oxygen plus another half an oxygen, which gives me a whole oxygen molecule. And I've got carbon dioxide. I have achieved my target equation. All right, this is the target equation. All right, so now that I have the correct target equation, I can now apply Hess's law. All right, and so what Hess's law states is that the delta H of combustion for this reaction is equal to delta H1 plus delta H2, making sure that the delta H values I use are the ones that I've manipulated through the process. So the first one is negative 110.5 kilojoules. And my second one is negative 283.0 kilojoules. Adding that up, I get an answer of negative 393.5 kilojoules. Okay, so I have solved for this particular reaction without actually performing the experiment. All right, let's do one more example so we get some practice in how we do these. All right, so looking at example number 2, we wish to determine the enthalpy change for the formation of 2 moles of nitrogen monoxide from its elements. All right, this is my target equation. And I want to find the delta H, or enthalpy change. I've been given these two equations. These are my given equations, or known equations. Okay, the known equations or given equations is what we're going to use, because we can then use their delta H's and apply Hess's law. So looking at my first equation, equation number 1, I look to this equation and see where is the important information. The important information here is the N2. The N2 in my target equation is part of the reactants. So it's on the correct side, so I don't have to reverse it. However, the actual coefficient is not correct. So I'm going to have to multiply number 1 by 2. And so I've got to multiply that whole equation by 2, leaving me with N2 plus 2 oxygens and 2 NO2s on the product side. Now don't forget, we must apply this multiplication as well to my delta H value of positive 34 kilojoules. Okay, so 2 times positive 34 equals positive 68 kilojoules. All right, looking at equation 2, again, we see that the reactant or product that's in my target equation is actually the NO. All right, so we notice that it's not on the right side. Okay, so we're going to need to flip it as well. You'll notice that the coefficients is not the same. So for the second equation, we're going to also need to multiply by 2 and flip it. You're going to need to flip the equation. Okay, and so as I mentioned earlier, you should always keep your arrows lined up so that you can add them up easily then. Add them up and cancel things out. So what this leaves me with then is 2 NO2s, 2 NOs, plus an oxygen. Sorry, I've run out of space here. And so my delta H2, I've got to apply the same thing. I'm going to times it by 2, as well as changing my sign. Okay, I'm changing my sign from negative to positive because I flipped it. And then multiply it by 2 to get an answer of positive 112 kilojoules. So that's very, very important to remember. All right, so now I'm going to go ahead. Now that I've manipulated my two equations, let's see what we can cancel out. And we're going to add them up. So I got 2 NO2s on the left and 2 NO2s on the right. So those two cancel out. I have got 2 oxygens on the left, but 1 oxygen on the right. So one of these cancels with one of these, leaving me with 1 oxygen remaining. Now I can go ahead and add up these two equations. I get N2 plus O2 makes 2NO. Have I achieved my target equation way up here? Yes, I have. So since I achieved my target equation, I can go ahead now and add up the delta H values for this particular reaction. So therefore, delta H for this reaction is delta H1 plus delta H2. And so I've got positive 68 kilojoules plus positive 112 kilojoules. And when I add it up, I get positive 180 kilojoules for this reaction. And that is my answer. All right. Let's try one more example. It's good to get practice doing these. The next one's a little bit trickier because we've got fractions, and I know how much students detest fractions. But let's work through it because a lot of our thermochemical equations actually do have fractions. So you have to know how to manipulate them as well. Pretty simple, just adding and subtracting fractions. So you need to make sure you've got common denominators. All right, so let's take a look at this final example for today, which is example number 3. We wish to find the delta H for this given reaction. All right, so therefore this is my target equation. We've been given these equations, and so these are the ones we need to manipulate. All right, so looking at the first one, we look to see which of the reactants and products are in my target equation, and we see that it is the NO2. We notice that it's on the same side as my target equation. So for equation 1, we're going to leave it. So I'm just going to rewrite it down here below, just so that we can then manipulate the equations that we are going to do here. Okay, so writing the equation as it is, and then including the delta H value as it is as well. Okay, so we don't do anything, because we didn't do anything to the given equation, we are not going to do anything to the delta H value either. Looking at the next equation, we see that we've got H2, O2, H2O. It is the H2O, the one is that we're interested in. It is on the correct side of my target equation as part of the products. However, it has a coefficient of 3/2. So for the second equation, we're going to have to multiply the entire thing by 3 over 2. All right, so that's what I'm going to do for my next equation. Okay, so I'm going to put 3 over 2 H2, and now I'm multiplying 3 over 2 times a quarter, which is going to give me 3 over 4 oxygens. All right, does everybody see that? So 3 over 2 times a half is 3 times 1 is 3, 2 times 2 is 4. That's how I got the 3 over 4. And now I'm going to put a 3 over 2 in front of H2O. Now don't forget, you need to apply this multiplier to your delta H value as well. So we got to go 3 over 2 times negative 241.8 kilojoules per mole. And when we work it out, we get negative 363.7 kilojoules per mole. All right, so 3 times negative 241.8 divided by 2. So make sure you got your calculator nice and handy. All right, looking at my third equation now that was given, we look to see what is the important, bring that back down, to see the important compound, and that is actually the ammonia. All right, so the NH3. Well, notice that the NH3 in my given equation is as a product, while in my target it is part of the reactants. So for this last equation, I need to flip it. The coefficients are good, so I don't need to do any multiplying. I'm going to flip it or reverse it. So looking at my last equation here, I am going to reverse the equation. Again, nice to line them up so that you can visually see what reactants and products are for our canceling purposes. And so when we do this delta H, folks, it's very important that we also change the sign. So the sign is negative 45.9. We're going to make this sign positive 45.9 kilojoules per mole. Okay, now we can go ahead and add up our equations. We're going to cancel anything that's common to the left and right side of the equation. So we notice here, folks, I've got a nitrogen molecule and a half nitrogen molecule. They cancel out. I have 3.5 hydrogens to 3.5 hydrogens. And do I have anything else that can cancel? No, I do not. However, now I need to go ahead and sum these up. So we'll notice that we can add up this 1 oxygen to 3 over 4 oxygen. So what you should do is make this 4 over 4. Because when we add, we got to make sure we got a common denominator. And 4 over 4 is just like saying 1. Hence, this is going to give me 4 over 4 oxygens plus 3 over 4 oxygens gives me 7 over 4 oxygens. And then I've got this ammonia as part of my reactants. Going over to my product side, I've got 1 NO2 molecule, and I have 3 over 2 H2O. Is this my target equation? Yes, it is. All right, so if we scroll back down there, we see that it is actually our target equation. So now we can go ahead and apply Hess's law. So therefore, delta H for this reaction is equal to delta H1 plus delta H2 plus delta H3, making sure that the values that we put into Hess's law are the ones that we've manipulated. So you'll notice that the first one we just left it as it is. So it's positive 33.2 kilojoules per mole. plus negative 363.7 kilojoules per mole, and plus the positive 45.9 kilojoules per mole, because that's the one we've reversed, so we had to change the sign. Now we go ahead and add them all up, and we get an answer of negative 283.6 kilojoules per mole. So we have now found the delta H for this reaction. All right, so this process does definitely need practice. I highly encourage you to read section 5.4 and then try these particular questions. The minimum that you should complete is on page 317, numbers 1 to 3. If you wish to do some extra practice, you can continue to do the questions. So these can be for extra, but these are the ones that I'd like you to complete as a minimum. All right, good luck, and we'll see you in the next lesson.